Hello everybody, welcome. This is paper 2 from May 2024 and this is time zone 2. Let's have a look and see what we can do. Alright, here we go. Starting off with a probability question. In a given week, the number of students in a particular primary school that were absent due to head lice, influenza, and/or chickenpox were recorded as follows. The primary school has 500 students. After this, they provide a breakdown of how these 500 students are distributed. When we read this, we just have to be careful of these words, which provide some additional kind of designation. So 35 students had head lice only, 20 students had influenza only, 5 students had chickenpox only, 4 students had head lice and influenza, and we have to be careful as well, but not chickenpox. 2 students had head lice and chickenpox, but not influenza. 3 students had influenza and chickenpox, but not head lice, and 1 student had head lice, influenza, and chickenpox. All right. The first question they ask us is to draw a Venn diagram to represent this information. So I'm going to go ahead and provide a box here. Make sure you do box in your values. When you're drawing a Venn diagram, you will lose 1 mark if there's not a box provided. If you just draw, let's say, the sets, the circles, for example. Alright, so since we're dealing with head lice, influenza, and chickenpox, we're going to need 3 separate sets. So I'm going to go ahead and draw 3 circles. Alright, should do, hopefully this will be big enough, I think so. Alright, so they provide us with some values H, I, and C for head lice, influenza, and chickenpox, respectively. So let's go ahead and use those. Head lice, influenza, and chickenpox. Alright, so let's go through this. 35 students had head lice only, so that would be this area right here. So although this area refers to all individuals with head lice, it's possible for someone to have head lice and influenza, head lice and chickenpox, or all 3. In this case, it's just only, so it's just these 35 individuals all by themselves. 20 students had influenza only, that'd be these individuals. 5 students with chickenpox only, and we can follow that same logic. 4 students had head lice and influenza, so head lice and influenza, but not chickenpox, so that would be these 4 individuals here, head lice and influenza. 2 students had head lice and chickenpox, right here, but they didn't have influenza. 3 students had influenza and chickenpox, but not head lice. That would be these 3 right here. And lastly, there's this 1 student that had head lice, influenza, and chickenpox. Rather unfortunately, I guess. Okay. Our Venn diagram isn't actually complete yet because there are some individuals that don't have any of these conditions. So there's 500 students in the school. There's some that have head lice, influenza, chickenpox, and out of all of these individuals, this doesn't look like it, doesn't add up to 500, but we know there's 500 absences. So how many individuals are outside of these conditions? How many of these individuals or these absent students don't have any of these conditions? Well, what's left over after our 500 students? These are the ones that are accounted for. Some are left over. So let's go ahead and add up all of the individuals with some of these conditions. So these 35 plus 4 plus 20 plus 1 plus 2 plus 3 plus 5. All of these individuals are accounted for. They have head lice, influenza, or chickenpox. And if we add this up, it should equal to 70. There are 500 students altogether, and we know that 70 of them are accounted for within these sets. And that means that 430 are left outside. These are the students that, well, don't have any of these conditions. And altogether, all of these values should add 500. Alright. Part B asks us to calculate the number of students who did not have head lice or influenza or chickenpox. I thought when I was reading this question that it was somewhat strange. partly because I feel like, in some sense, this first question, draw a Venn diagram to represent this information. The Venn diagram is itself incomplete insofar as we didn't have this. It would be incomplete if we didn't have the number of students who did not have head lice or influenza and chickenpox. But part B is asking us to find that missing piece, this missing piece right here. So there it is. I would just say one final thing. Sorry. One final thing is that given that this is a 2-mark question, we would need to show the sum of values. So if I can just bring up the mark scheme just really quick. Here it is. We see, even though it's a rather basic calculation, 35 plus 4 plus 20, since it's a 2-mark question, they're expecting to see some kind of process. So 35 plus 4 plus 20, adding up all these values on the inside, is equal to 70, and of course, well, 500 minus 70 gives us this 430 on the outside right here. All right, let's continue on. A student is chosen at random from all the students in the school. Find the probability that this student has head lice. So this is C1. This is probability of head lice. Remember, for a simple event, for a single event like this, it is number of desired outcomes over total number of outcomes. In this case, there are 500 individuals in the school. And let's find out how many have head lice. So how many have head lice? It's all of these students within here. So not just the 35, but every single one of these, even the students that have head lice and influenza and so on. So 35 plus 4 plus 1 plus 2, this would add up to 42 students altogether. So I don't know if we need this, but just to be a little clear, all of these students, all of these within here added up together, these are the individuals with head lice, and there are 42 individuals. So 42 out of 500, if we want, we can simplify, not necessary in this case. I would just say one last thing. Probability can be shown as a decimal, fraction, or percent. So if you wanted to, you could also write it as 0.084 and so on and so on. Okay. Let's go on to part 2 of this question. Find the probability that this student has influenza given that the student has head lice. All right. So for this question, there are a few different ways that we can solve it. We can go to the formula booklet, and we will actually have a conditional probability formula that we can use. But I think sometimes it's easier to use some intuition, and I'll show you that in a sec. So whenever we see that given that, we know we're in the realm of conditional probability. So let's actually go to the formula booklet just really briefly. Here we are. Here we have conditional probability. It is given by probability of A given B is the intersection of A and B all over PB. So let's try to unpack what that means a little. Okay. So in this case, we're asked to find the probability that a student has influenza given that they have head lice. So let's actually use intuition first, and then we can use the formula. So what I like to do for these kind of questions is read it from the back to the front. So given that the student has head lice, what's the probability that they have influenza? Okay, so probability that they have influenza given that they have head lice. So given that we're dealing with the students that have head lice, that's our subset in some sense. So we have 500 students all together in this school. How many of them have head lice? Well, we found this earlier on, and it was 42 students that had head lice. So given that a student has head lice. So now given that we've got those 42 students with head lice, we've asked them to come forward in a way. Out of these 42 students, how many of them have influenza? So let's go and look back to this section right here. So we have these 42 students, and these are the students, this 4 and this 1. So these 5 students right here, these 5 out of 42 students are the ones that have influenza. So once again, given that a student has head lice, given that we've got these 42 students, out of those 42 students, how many of them have influenza? And it was, well, 5 out of 42. Okay. And I think that is the easier way to do this. If we wanted to use the formula booklet, influenza, given that they have head lice, we could find the intersection between influenza and head lice all over head lice. And of course this works actually if you just replace probability with number, of course. And that would work as well. So the intersection between influenza and head lice. Influenza and head lice. I don't know if I can erase this entirely. That's not a good idea. So the intersection of influenza and head lice, just to show it once again, would be these individuals, influenza and head lice. So I and H, the overlap, would be this 5. Over the number that have head lice, and once again, number that have head lice is 42. So I suppose they're both okay. If you're comfortable using the formula booklet, there it is, intersection of influenza and head lice over head lice. Thinking about it through intuition, potentially versatile when it's a little unsure, but 2 different ways, I suppose. 5 over 42. Alright, so rounding out this question. Diego is a teacher in the school. He believes that the number of students n who have had influenza during the first t days of the school year can be modeled by the function number of students as a function of time is equal to 250 minus 240 multiplied by 2 raised to the power of kt, where k itself is some real number. That means it can be any value, actually. It could be, in some sense, positive or negative in that sense. That's right. All right, so let's go on. Use Diego's model to calculate the number of students who started the school year with influenza. So this is a super common question dealing with exponential equations or exponential functions. They ask us to find some initial value. And whenever we think of initial value, we should think, well, what is that when t is equal to 0? So we've got this function here, which relates the number of students with influenza to the time, where we put in some value of t for time as our input, and as the output, it'll tell us the number of students. So this is our function right here. But what happens when t is equal to 0? How many students started the school year, that is to say when t was equal to 0, with influenza? So let's go ahead and substitute 0 in for t. 240 times 2, and then this is going to be k times 0. Of course, k times 0 itself would become 0. And then 2 raised to the power of 0. We know anything raised to the power of 0 just becomes 1. So we have 250 minus 240, because remember, this right here would just become 2 to the 0, which itself goes to 1. So 240 times 1. And we'd be left with 250. Jeez. Okay. 250 minus 240 would leave us with just 10 students at the start of the year. All right. Let's go on to question E. It is known that 130 students have had influenza during the first 10 days of the school year. Find the value of k. So this is actually, again, a pretty common sequence that we'll often see with exponential equations. Is they'll ask us to find some initial value, and then they'll ask us to find some unknown, k or a or something like that, when giving us a value. So in this case, they gave us a value of t is equal to 10, and they gave us this value of n is equal to 130. So this original function right here was relating number of students with influenza to time. And in this case, they're giving us a value for n, and they're giving us a value for t. And with that, if we substitute, we should be able to solve for this unknown right here. So let's go ahead and write it out. I'm going to write it out slightly differently. I'm just going to write it as n, number of students, is equal to 250 minus 240, 2 times kt. And so we have essentially one unknown, two unknowns, three unknowns. But since we have 2 out of the 3 unknowns, we should be able to solve, and then we'll just have 1, and then we can end solve. So n is equal to 130. What else? T is equal to 10. Okay, just grabbing these values right here. Okay. After that, we just have k as one unknown. So let's go ahead and solve for k. All right, I'm going to go to the calculator here and work that out. All right. Menu, algebra, numerical solve. And then let's write out what we have. 130 is equal to 250 minus 240. 2 raised to the power of k, and then t at this time was 10. I'm going to put a multiplication symbol just in case. And let's ask it to solve for k. In this case, k is equal to negative 0.1. Alright, let's go back to the document. Okay. K is equal to negative 0.1. Alright. Let's keep going. Using this model, calculate how many days it will take for 200 students to have had influenza since the start of the school year. Okay, so here we are with F. So we're beginning to build out this model. We're relating the number of students with influenza as a function of time, and originally it was 250 minus 240 multiplied by 2, and we didn't know what k was. But now we know k is equal to negative 0.1, so we can actually substitute this value and write negative 0.1 multiplied by some value of t. And in this case, remember, this is a function which relates inputs and outputs, so I'm actually going to erase this and write n. So we can plug in some value of t, which is an input, and it will tell us the number of students that have had influenza up until that time. But there's nothing to say that we couldn't plug in an output. That is to say, there's 200 students, at what time would that occur? So remember, this is a function that relates inputs and outputs. We know one of them, one of the two, we can solve for the other. And in this case, we want to know the time that it will take for 200 students to have an influenza. So when n is equal to 200, what would t be in order to make this 2? Alright, so in order to make this true, what value does t need to be? Then we can go ahead and end solve this once again. Okay, I'm going to go back to the calculator here. Menu, algebra, numerical solve. Oops, there we go. In this case, 200, that's our output. And we want to ask the question, what is the value of t required to make that true? I'm going to put a multiplication just because sometimes it doesn't work otherwise. Okay, this looks good. So 22.63 days. Let's write it as, let's go back to the document for a sec. T is equal to 22.63. So it's 22.6 significant. So when we write it to 3 significant figures, 3 sig figs would be 22.6. Just looking at the mark scheme here, there's no requirement to round up. And you might say intuitively that it's not until 23 days, it's not until the 23rd day that we have, well, 200 students absent. So definitely don't round down. But just looking at the mark scheme here, the IB does accept 22.6, and in this case they do accept the rounding of 23 as well, if that is your intuition. Alright, ending off here, by the last day of the school year, it is known that 300 students have had influenza. Comment on the appropriateness of Diego's model. Okay, so Diego's model tracks the number of students who have had influenza. So not the students that have influenza at any given time, but who have had influenza. And if we look at this situation itself, there's going to be this equation itself. We have 250 minus some value right here. And this, since this is an exponential, minus 240 times 2, and then raised to the negative 0.1, this value right here is always going to be positive. It's always going to be positive. So our exponentials are something like this. In this case, if it's a negative, if this k right here, since this k is a negative right here, k is a negative, I'll just say because k is less than 0, we're going to get some exponential like this. It's going to go down and it's going to approach 0. But it's always going to be something. It's always going to be positive in some way. So if we have 250 minus some positive, even if this thing goes to 0, we're going to be left with, well, 250. At the end of the year, maybe, potentially, or after some time has passed, we're going to have 250 individuals that are going to have influenza. But it looks like, for example, at this school, there might only be 250 students. So this question, where it says, by the last day of school, it is known that 300 students have had influenza, this model doesn't go up to 250. It doesn't go up to 300. It only starts, it will only go to 250. So in this case, this is the value that we're taking away from. This is what the model might look like. It might have some kind of asymptote. So there's some students getting sick, and then after a while it plateaus at around this value of 250. If I can draw this here, and y is equal to 250. So we never go above this point. What you can try to do is if you substitute 300 in here, I believe it will return an error as well. So we're not going to ever have a point where n is equal to 300. And so if we want to provide a comment on the appropriateness of Diego's model for part G, what we could say is the model does not reach 300. The model only maxes out at 250. So the model does not reach 300 students. And if we wanted to, we could say maximum is 250. All right. All right, question 2, 14-mark question. Looks like a coordinate geometry question. Maya is at an amusement park. A map of part of the amusement park is represented on the following coordinate axes. Maya's favorite 3 attractions are positioned at A, 0, 16, B, 12, 20, and C, 12, 0, which is all the way down here. All measurements are in meters. So it looks like we've got, well, part of the amusement park, and the y-axis represents our northerly direction that we travel, and then the x-axis is the easterly direction that we travel. Part 1 asks us to write down the distance between B and C, and importantly this is a 1-mark question, so it should be fairly straightforward. So distance between B and C, we can see that's just this distance right here. Distance between B and C, we start at 20, going all the way down to 0. the answer in this case would just be 20. So I'm going to write that here. BC is equal to 20 meters. On a test, you could actually, in this case, just write 20, but there it is. BC is equal to 20 meters. Okay, part B, calculate the distance between A and B. I'm going to erase this here. Oops. The distance between A and B, that is this distance right here. So that's what we're trying to find. And if we look at this, we actually have a right angle triangle, or at least we can create one. And once we have a right angle triangle, we can use Pythagorean theorem. So working out these side lengths right here, if we are going from 0 to 12, we know that this distance right up here would be equal to 12. And similarly, if we're going from 16 to 20, or 20 to 16, this distance right here, write it like this, would itself be equal to 4. Alright, from here if we label this, let's call it C, we know that our Pythagorean theorem is small side length squared plus other small side length squared is equal to, well, the hypotenuse squared, or a squared plus b squared equals c squared. Alright, just rearranging, I'm going to actually write this out because sometimes I think it's helpful. Squared, just write out c, take the square root of both sides to just get c all by itself, and now we have 4 squared plus 12 squared, and we can work that out on the calculator. Of course, you could actually just end solve this, and that would work as well. Okay, I'm going to go to the calculator and work this out. Here we are. Going to write this as a square root, and let's write 4 squared plus 12 squared. The answer is 12.649. 3 sig figs, that would be 12.6. Alright, so I'm going to head back to the document here. And C is equal to 12.64, 12.6 to 3 sig figs. Calculate the distance between A and B. More technically, I guess we could write this as AB is equal to 12.6 meters. Okay, 2-mark question. Just be sure to show process, show at least this relationship, or carrying out the Pythagorean theorem. Okay, let's move on. Here we go. Mai is standing at the attraction at B and wants to walk directly to the attraction at A. Calculate the bearing of A from B. A from B, okay. So she's standing at B and she wants to walk to A. Okay, let's go back to here, clear up some space, and have a look. Okay, so she's standing at B and wants to walk to A. What is the bearing of B from A? Is that the question? The bearing of A from B. Okay, A from B. So here she is at B. She wants to walk to A, and we want to know the bearing of A from B. Of A from B. Okay, so first off, what does that mean? What are we talking about when we're talking about bearings? Bearings is essentially the angle that we need to sweep through going from true north. So I'll just draw one kind of setup, I suppose. So we imagine this is true north, and let's say our bearing is 60 degrees. What does that mean? That means relative to true north, which is this value right here, what angle do we need to sweep through? So here this is a bearing of, for example, 60 degrees. That would be a bearing of 60 degrees. Another example, always relative to true north, our bearing of, let's say, 120 degrees. So this one was 60 degrees once again. 120 degrees is sweeping through an angle relative to true north. Oops, I don't need that. Relative to true north of 120, and then we head off. And in this case, the question that they're asking is, if Mai is at this point B, and she wants to go to, if we're asked about the bearing of A from B, so we want to go to A from B, what is the bearing that she needs to sweep through? So here's true north. What is the bearing that she needs to sweep through, or the angle that she needs to sweep through to go to A from B? So the bearing of, we would say, A from B. That's what it says here, the bearing of A from B. So we're going, sometimes I think it helpful to read these from the back to the front. So we're going from B to A. And the question is, what is the angle that we need to sweep through? B to A, what is the angle that we need to sweep through? Okay, so let's go ahead and see how we can work this out. So first off, we know that this right here is part of, well, angles on a line. So this is just going to be a full 180 degrees. And the question is, okay, well, what is this remaining part? So the full bearing is going to be 180 plus, and then we could say, let's get this back, this theta value here. So 180 plus theta, that would be the angle that my would need to sweep through before heading off to A from B. So how can we do that? Remember, a good IB question often doesn't ask you to solve something just in isolation. Often what we have done in the past, we can make use of, or they would like us to make use of, especially on a paper 2, in later questions. So although I erased it here, we know that AB is 12.6. So AB, remember, is 12.6. And I think that actually will be helpful. So AB is equal to 12.6. And let's go ahead and draw another right angle triangle, this time this way. And in this case, if we have theta right here, then how can we potentially find, or sorry, if that is our theta, how can we potentially find, theta? Well, a right angle triangle, we would need 2 side lengths, and we actually have all 3 side lengths in this case. We know that this right here was, remember the original question, this was equal to 12, just going down here. And this also, part of our original question, was equal to 4. So we actually have all 3 side lengths. It doesn't really matter which trigonometric relation we use, because we can use either one. For this, I'm actually going to use the opposite and the adjacent, because those we know exactly. 12.6 we've rounded, so I'm going to use 4 and 12. Remember SOHCAHTOA? SOHCAHTOA. This is actually not in the formula booklet, our trig ratios. So in this case, going to use the opposite side length and the adjacent. That would be opposite adjacent. So tan theta equals, in this case, opposite is 12 and adjacent is 4. You can go ahead and end solve this, or a little more technical, I suppose, we could take tan inverse of 12 over 4. Alright, I'm going to go ahead and go back to the calculator, and I'll show you how to end solve this just in case that inverse is maybe a little intimidating or so. Alright, in this case we have, let's go trig tan, let's call this x, is equal to, and then we'll set a fraction as 12 over 4. And then we're going to solve for x. Always make sure you're in degrees, and then we'll see what we have. 71.565, or 71.6 degrees. Okay, I'm going to go back to the document. Theta is equal to 71.6 degrees. Alright, so before we talked about the angle that we needed to sweep through relative to true north to head off from B to A, or we would say A from B. And in this case, it's going to be 180 degrees plus this theta value here. So let's go ahead and write that out. 180 plus this 71.6. And this is going to be the value that we need to sweep through. And this is going to be 280 and 51.6 degrees, or to 3 sig figs, 252 degrees. And that would be enough. Okay, I think that was a 3-mark question. Yeah, calculate the bearing of A from B. This would be the angle that we need to sweep through. In terms of process, I'd imagine a tan relationship showing 180 plus 71, and then our final answer. Okay. Part D, there's 3 parts to this. A drinking fountain is to be installed at a point that is an equal distance from each of the attractions at A, B, and C. Write down the gradient of AC, write down the midpoint of AC, and hence calculate the coordinates of the drinking fountain. So first off, 8-mark questions. It looks like we have the goal, which is to install or find the position of the drinking fountain that is an equal distance from each of A, B, and C. And then they've got a little scaffolding for us. The gradient of AC, the midpoint of AC, and the coordinates of the drinking fountain. Okay, so let's go back up here. I'm going to clear this canvas, and then we'll work with this here. Okay, so first question, they asked us to find the gradient of AC and then the midpoint of AC. So here's AC. Let's find the gradient of AC. Remember, we can go to our formula booklet and find the slope formula. Slope formula is given by m, and that's equal to y2 minus y1 over x2 minus x1. Conventionally, we call this rise over run, and we can plug in values of y2 minus y1, x2 minus x1 like this. I think, to be honest, if we want to find AC, a nice way to do it as well, since we've got this coordinate grid, is actually just to create a triangle. And I'll show you what I mean by that. So here is one part of our triangle. Here's another leg of our triangle, and this is the direction that we head off in. So if a slope is itself just rise over run, what have we done? Essentially, it's every move to the right leads us to do what? And in this case, we've gone down 16, so we've gone down negative 16 for a run of 12. And if we wanted to, we could write this as negative 16 over 12, just like that, which would itself simplify to, would it be 4, 8, 12, 16, negative 4 over 3. And so I think that's always helpful. A move to the right, once again in a different way, I suppose. A move to the right of 12, that would be our run of 12, leads to what? Well, a rise, or in this case a fall, of negative 16. So essentially up-down movement over horizontal movement. That's one way to do it. If you're more comfortable with the formula, that's always an option as well. In this case, just label your points. Here we go. A itself is 0, 16, and C itself is 12, 0. y2 minus y1, let's label these just for, I guess, to be safe. y2 minus y1 over x2 minus x1. This is negative 16 over 12. Oops, negative 16 over 12, which is, once again, negative 4 over 3. So both of these will give you the equivalent result. Alright, so there is our slope. Slope is equal to negative 4 over 3. I'm going to go and write that in. M is equal to negative 4 over 3. Write down the midpoint of AC. The midpoint, remember, is also given in our formula booklet under coordinate geometry. I'll actually bring that up now. Here we are. Let's go into, here we are. Where is it now? midpoint, here we go, coordinates of the midpoint. So average of the x's, and then average of the y's. So x1 plus x2 over 2, and y1 plus y2 over 2. Alright. Here we go. Okay, so let's go ahead and write that out. I'll write it out under here. So the midpoint, remember, given by x1 plus x2 over 2, and then y1 plus y2 over 2. In this case, we've already labeled these values, so let's add them up. 12 plus 0 over 2, and then we have 0 plus 16 over 2. This is going to be 12 over 2, which is just going to be 6. And this is going to be 16 over 2, which is just going to be 8. And that is our midpoint, essentially the halfway point between this and this. Alright, that would be 6, 8. Alright, last part, and this is the big one right here. Hence, calculate the coordinates of the drinking fountain. So the drinking fountain, we wanted an equal distance from both A, B, and C. And the question is, okay, well, they just asked us to find the midpoint between A and C, which is at 6, 8, which is right here. And they just asked us to find the gradient, or the slope, right, the direction that we, I guess that's our rise over run. The direction that we head off into, I suppose, but I don't know if that's a good way to describe it in this context exactly. So we've got the midpoint, we've got the slope, and how can we use that to find the point that is going to be an equal distance away from both A, B, and C? And we can guess that it might be somewhere around here, I suppose. That would be an equal distance from each of these. But how can we make sense of that? This is, in some sense, actually a Voronoi type question. And it's something like what's called the nearest neighbor in a way. So if we wanted to, for example, to construct some kind of Voronoi using these three sites, A, B, and C, we would create perpendicular bisectors. So just looking at B and C, for example, B and C are 20 apart. The perpendicular bisector between B and C would be this line right here. So I'm going to just sketch it out. So perpendicular bisector between B and C would be, actually maybe I'll just see if I can do this actually. That's okay. That's not bad. So that would be the perpendicular bisector between B and C. And what that would mean is that any point along this line is an equal distance from B and C. Even this point right here, it would be an equal distance from both B and C. What I mean by that is, if this is a distance, we're still on the line, and we're an equal distance from both B and C. Any point, and that's going to be true of any point along this line. We're going to be an equal distance from B and C. And in a similar way, let me just clear this up. In a similar way, if we were to have the perpendicular bisector of, let's say, A and C, because we already know the midpoint, we already know the slope. If we were to have the perpendicular bisector, so let's maybe just imagine what that might be. This is AC. Let's try to draw a right angle. Maybe something like this, I suppose. A right angle. That looks pretty good. Maybe I'll try to extend it the other way. Okay. So along this line, again, any point along this line, or if we've drawn it correctly, would be equivalent distance away from both A and C. So here we're an equal distance from A and an equal distance from C. And if we want to find the point that is an equal distance away from both A, B, and C, it would actually be the intersection of these perpendicular bisectors. So to draw one more, just looking at this, this looks like a midpoint of BC. This would again be our perpendicular bisector between A and B. it actually happens to just intersect, but that's maybe just an accident. I mean intersect C right here. It's not an accident that it intersects here. But all of these points are going to be an equal distance away from A, B, and C, this point of intersection. So hopefully that's decently clear. So I don't mean to go over this in too much detail, but any point on the line right here is going to be an equal distance from A and B all the way up to this point as well. We're going to be an equal distance from A and B. Similarly right here, this is going to be hopefully not too messy. When we're talking about C and B, any point on the line here is going to be an equal distance between B and C. And we can generalize that to when we're, well, right here and here. This is also going to be an equal distance from B and C. And what we find is, no, don't think we need to do this for A and B, but what we find is that if we find the intersection of these perpendicular bisectors, then we find the point which is, by definition, not just an equal distance between B and C. That is to say, not just an equal distance from B and C, but also an equal distance from A, B, and C, an equal distance from all three. Okay, and so the question is, well, what is that point? Let's go ahead and find out. So we already know one thing. We know that, I'm just going to move this aside. We know that the perpendicular bisector of B and C is y is equal to 10. This is 20, this is 0 right here. We know a horizontal line. Remember, a horizontal line is just y is equal to something. So y is equal to 2, for example, would be something like this. This is y is equal to 2. It's just a horizontal line, and then this is x is equal to 2, for example. So we know one of these perpendicular bisectors already is y is equal to 10. And we've already got a start on this perpendicular bisector. That is to say, we know the midpoint and we know the slope. So let's go ahead, find this other perpendicular bisector right here, and then find the intersection, and that will give us this point right here. So let's go ahead and start off with our equation of a line. Y is equal to mx plus b. Now we know the slope of AC right here is equal to negative 4,3. So if we want to find our equation of our perpendicular bisector, let's begin with this m right here. We know m itself is equal to negative 4/3, but we want to find m perp, that is to say the perpendicular of negative 4,3. So remember, switch the top and the bottom and then multiply by negative 1. So in this case, we're going to switch 3 and 4, and I guess it used to be a negative. I guess we could put it right here. And then what we want to do is multiply by negative 1, and that would, of course, turn it back into just 3/4. So switch the top and the bottom, multiply by negative 1, and we're left with 3/4. And that's a line that is perpendicular to AC. So we've got y is equal to 3/4 x plus b. Now we've got 1, 2, 3 unknowns, but we do actually know one point on the line. And remember, if a point is on the line, then it satisfies the equation. So let's go ahead and substitute the midpoint, which we found earlier. So we know y is equal to 8 when x is equal to 6. And now we've reduced 3 unknowns to 2 unknowns, and we can go ahead and solve for b, and that would be the last piece of the puzzle. I'm going to go ahead, we can actually work this out using a calculator, or we can end solve this, to be honest. I'm going to do a little algebra here. 3/4 times 6, and then we'll take 8 minus that value, and this will be b is equal to 3.5. Or if we wanted, we could say 7 over 2. All right. Okay, let me just make sure that's all good. 3 over 4 times 6, 8 minus, yeah. Okay. Good. So we found that last piece of the puzzle, the y-intercept, which is 7 over 2. And just to be sure, we said it's roughly 3 over 5, and that doesn't look too bad. That's can maybe be somewhat reassuring. So let's go ahead and write out that equation of a line. Y is equal to 3 over 4x plus 7 over 2. So we've got this equation, this red one right here, this perpendicular bisector. Okay, so we've got one equation, we've got another equation, and then the question is, where do they meet? That is to say, when does y1 equal y2? And we can do this in two ways. We can graph both of these and then find the intersection, or we could just essentially ask that question. When does y1 equal y2? Or that is to say, when does 10 equal, and remember this right here is y2, 3 over 4x plus 7 over 2. And now we've got an equation with just one unknown, and we can actually end solve for that. So that's another way. That's probably the more algebraic way. I'm going to go to the calculator, and I'm going to actually graph these two functions and find the intersection that way. So here is y2, or this perpendicular bisector of AC, and here is y1, which is just the perpendicular bisector of this line right here. So I'm going to graph those and then find the intersection. Alright, so here's a calculator. Let's go into graph, and let's put in 3 over 4 x plus 7 over 2. Okay, and let's get another graph menu, graph entry, function. And this one we just want to say is equal to 10. So remember, this f of x is the same as y, more or less. Alright, and it's actually off the window, so I'm going to zoom out. So if you type something in, you don't see it, zoom fit or simply zoom out. Alright, let's analyze graph, find the intersection, hover over, and there it is. 8.6666666, so on, and 10. That is the ideal location. So I'm going to go back to the document and write that out. So the ideal location is 8.67 and then 10. And that would be the ideal location. And just to check again, 8.667, 10, that looks to be about right. It's just based on our estimate. So let's see, hence calculate the coordinates of the drinking fountain. Coordinates are 8.67 to 3 sig figs, and the y coordinate is 10. Okay, so I think pretty involved, 2-mark question, fair bit actually going on. I would say kind of a hidden Voronoi and then some bearings, so yeah, some good challenge here. But once again, this intersection of perpendicular bisectors is going to be the point that is an equal distance. Remember, an equal distance from all 3 of these sites. All right, good question, I think. Okay, number 3, 15-mark question. It actually looks like a trapezoid rule question. Let's see. The following diagram shows a model of the side view of a water slide. All lengths are measured in meters. So we've got the height, and then we've got the width of this water slide. The curved edge of the slide is modeled by this function right here, f of x equals -1 over 4x squared plus 2x, And it's saying for when x is greater than 0 and less than 4. So this curved part up until 4, from 0 to 4. The remainder of the slide is modeled by, and then they tell us for when it's x is greater than 4 and less than 5. This point is just this straight line, y is equal to 4. And then for 5, when x is greater than 5 and less than or equal to 12, it's just this linear equation, 48 over 7 minus 4x over 7. This straight line, this linear equation right here. So we've got each of these sections of the water slide modeled by a different function. And they're asking us to use the trapezoidal rule with an interval width of 1 to calculate the approximate area under the model of the slide from this interval 0 to 4. Okay, so remember what the trapezoid rule does. It's used to approximate the area under the curve. So in this case, they're asking us to use a width of 1. And just to give a visual, what this would mean is we could find the height when we're at 1. And we could draw a trapezoid. And so it might look like that, or thereabouts. Let me actually just modify this slightly. Alright, so that would be our height, rather. And same with at point 2, just going straight up, there is another trapezoid. And at point 3, there is an additional trapezoid. And then at point 4, there's this final trapezoid right here. Okay, and if we can find the area of these trapezoids, then we can find a rough approximation of the area under the curve. Okay, so trapezoid rule, remember, is in our formula booklet. Let's go ahead and just have a look at that. Trapezoid rules under calculus. Here it is. Might look a little intimidating, but I don't think it really needs to be. So first off, this part right here, this is just our integration symbol, and it's saying the sum of all the tiny little squares, or essentially the area under the curve, starting at a, going to b, of some function. And then this is dx, this is those little squares. In theory, that's what calculus is doing. It's finding the sum of all these tiny little squares, in some sense, or rectangles rather. Alright, and it's saying that the sum of all those little rectangles from a to b of some function is approximated by, and this is our trapezoid rule, so 1/2 h. H looks confusing, it looks like they're giving us another kind of formula, but all it is the width of the trapezoids on the bottom. And in this case, they already gave us the width, it's just equal to 1. So that's already done for us. And then this is y0, yn. This is the height at that first location, so you can think of it as almost h0. And this is the height at the last location, this yn. That would be the height at the very end. And then we have 2 times all of the intermediate heights. Alright, and that, I think there's actually other videos where I've gone into the trapezoid rule in a little more detail, so I think this potentially is enough. This original h is just the width of our trapezoids. This y0 and yn is the starting and ending height, and this is 2 times all of the intermediate heights. So with that being said, let's give it a try. Oops, where did this go now? There we go. Okay, so I'm going to write out the trapezoid rule once again. Let's use this space. I think this is good. So we don't need to write this AB, and so I'm actually just going to write it out as 1/2 h, and then we have y0 plus yn plus 2 times y1 plus y2 plus ... plus all the way up to the second last. And then let's put some brackets around all of this. Just make sure, a common mistake is that students don't have brackets and they just multiply 1/2 h by this, and they don't multiply it by everything on the inside. So just be careful that you've got brackets right here. Okay, and let's substitute some values. So 1/2 h. H is just the width of these trapezoids, which is 1. The h b minus a over n is just saying end point minus starting point, 4 minus 0, over number of trapezoids, 1, 2, 3, 4. Over 4 is equal to 1. But what it really means is the width of these trapezoids. Alright, so 1/2 1. And then let's go ahead and find the height. The height at each of these individual points. So the height at the very beginning when x is equal to 0. And now when x is equal to 0, I mean, we've got this function right here. We can plug in 0, and it's just going to become 0 here. And when we plug in 0 into this is all going to become 0. I don't think we need to write that out, but I suppose I will. You can skip ahead if you see where this is going. So at point 0, what do we have? What is the value? 0 squared plus 2, 0. Well, when x is equal to 0, well, the y value is just equal to 0 as well. So this is going to be 0. And what about yn? Yn refers to that last point right here. So in this case, what is the y value? What is the height when x is equal to 4? So again, we could plug in this value of 4 for x, and then we could work it out like this. Since we actually need to do a fair number of values, I think we could either graph this function and then use the trace function to help us out, or the trace feature within the graph, or we could just write out this function and copy paste. I'm going to graph out this function, so let's go to the calculator. Here we go. So this is our function once again. -1/4, and this is x squared plus 2x. I think that's it. Okay, so obviously our function ends at 4. It doesn't keep going. We just have a portion of this. And I'm going to use the trace function to find the value of 4. So graph trace, and what graph trace is, it says, okay, give an x value and it'll find the y. So I'm going to type in 4 right here and then press enter. And so when x is equal to 4, y is equal to 4. That's the height. So I'm going to actually I'm going to write that in on the document as well. So when f is equal to 4, y is equal to 4. So we've got 0 plus 4 plus 2. Then I'm going to use the same idea. So still within the document, what is the height? What is y1? What is y2? Oops, can do better. What is y3? We already found what y4 was, with yn, the final one. So y1. y1 is when x is equal to 1. So I'm going to go to the calculator, graph trace, and plug in a value of 1. When x is equal to 1, y is equal to 1.75. That's the height. So I'm going to write that out, 1.75. And then let's look at y2 here. So when x is equal to 2, menu, trace, let's go to, here we go. This is 3. I'm going to write this out. Plus, and then the last one, menu, trace, graph trace. Actually, I don't think we need to do that every time. X is equal to 3 here. Alright, and that's 3.75. And then after that is 4, which we already calculated. I just want to actually see if we can type in 4. Yeah, we can. So we actually don't need to do graph trace. And that would bring us back to n, which we already found. So let's go back to the document here. And there is our estimate. So the estimate of the area under the curve of this function from 0 to 4 of f of x can be approximated by this thing right here. Okay, now it's just a matter of working that out. So I'm actually going to go back to the calculator once again and type this all in. So 1/2. We don't need to put 1, so actually I don't think I will. But I'm going to open up a bracket and 2 brackets actually right side by side. 0 plus 4, I'm going to include it. We don't need to head 0 plus 4, but we can. 1.75 plus 3 plus 3.75. There we are. So making sure this bracket here grabs everything. So this bracket and this bracket, we're multiplying everything by 1/2. Just be mindful of that. And I think we're good. So our answer in the end, our approximation, is 10.5. So I'm going to go back to the document and write that up. All right, so not too bad. Let's see what else we have. So area under the curve, I guess if we wanted, we could say meter squared, but 10.5 is enough. Okay, 5-mark question. It took a while, so I think that's fair. All right, 3-mark question. Find, and then this is, to be honest, it's not a bad question, but notationally it might be difficult to interpret. So what this means is find the integral, the indefinite integral of this function right here. So another way to say that is take the antiderivative of this function right here. This is in our formula booklet. We can go there and check. We're still in the realm of calculus. So this is the integral. Something going on. This is the integral, and it is essentially the opposite of the power rule. So just to provide, just remind you the power rule, remember we take n, multiply out in front, so there's an n, and then we reduce the exponent by 1. What an integral is, or to take the antiderivative, is we take some function. If we have f of x is equal to x to the power of n. If we want to take the integral of this function of, let's say, what they have is x to the n dx, or let's just say take the integral. Let's see if I can just erase this actually, and we'll just speak maybe more generally about taking the integral rather, and we'll call it big F of x. What we would want to do is we would want to increase, just like here we took n minus 1, we would increase our exponent by 1. But since when we take the power rule, we multiply out in front, in this case, if we plan on doing that again, we need to divide by n plus 1 just to compensate for the time where we're going to, well, multiply out in front. And so the integral is the opposite of differentiation. We reverse the process. Instead of multiplying out in front and adding 1, or sorry, taking away 1 from the exponent, in this case we add 1 to the exponent and we divide. So let's go ahead and see what that looks like. So here is our function. So I'm going to write it like this. F of x is equal to 1/4 x squared plus 2x. And we want to take the antiderivative, and we can actually write it as big F like this. Alright, so let's go ahead and let's look at this exponent. The exponent is 2. That means we want to increase it by 1. So we still have this negative 1/4 out in front, and we want to increase this exponent by 1. And this one might be a little challenging because what we want to do is we actually want to divide by 3. So whatever this value is that we increase it by, So we increase the 2 by 1, it's 3. And then we divide by that same amount. And to be honest, I actually don't think the IB is going to accept negative 1/4 over a third. So we're going to need to work with that. But maybe let's leave that for now at the moment. And then we're going to have plus 2. X used to be raised to the power of 1. So we still have 2x used to be raised to the power of 1. Now it's raised to the power of 2. And we're going to divide by that same amount. So now let's clean this up. Equals 1/4 divided by 3. So we're making it 3 times smaller. This 1/4, we're now going to divide it up into 3 equal portions. It's now going to be equal to negative 1/12. You can also actually just go on the calculator and go negative 1/4 divided by 3, and it'll give you the same thing. So now we used to have 1/4, negative 1/4 x cubed divided by 3. Now we have negative 1/12 x cubed, and then these 2's are going to cancel out. We're going to have x squared. And last little part, remember when we take a derivative? So if we have, let's say, f of x is equal to, I don't know, x squared plus 3, and we actually take the derivative, and it becomes, well, 2x, and that's it, plus 0, because our constants just fade away. Since anti-differentiation is the process of reversing differentiation, we actually don't know if we had a constant here originally. We don't know if there was a constant that when we took the derivative, if we were to take the derivative, would have just fallen away. So we add one here with c, this unknown constant that potentially was there actually. And that would be our antiderivative. All right, so I don't want to go in too much detail on this, but if we always want to test, if we ever want to test whether our antiderivative is actually correct, we can go ahead and actually take the derivative of this. Multiply by 3 would give us negative 1/4. X cubed would turn into x squared, which is good. And this x squared right here, multiply out in front, would become 2x, and this would become just to the 1, which is that we have 2x. And then this c, of course, would fall away. So yeah, it looks like we have reversed the process decently well. Okay, let's go on to part C. Calculate the exact area under the entire model of the slide from x is greater than or equal to 0 and less than or equal to 12. So we want to do the exact area. So the exact area. So we don't want to use the trapezoid rule anymore. We want to write out an integral for the exact area, and then we can find this area and this area if we want. So let's go ahead and do that. I'm going to clear this up, and I think I actually might actually clear this all and then use this as the canvas. Okay, I think that will be good. So here we go. We want to find the exact area. So let's go ahead and label these things. A1 plus A2 plus A3. So the exact area, let's maybe work from least to most challenging, I suppose. Let's do this A3 first. There's a few ways that we could do this, but I think this is going to be potentially the easiest way. This A3 right here, it's essentially a triangle. And we're going from 5 to 12, which means this triangle has a base equal to 7. So 5 plus 7 is equal to 12. And we know that this was at 4 right here. And it has a height. This triangle has a height of 4 as well. So essentially what we have for A3, so I might need this space later on, so maybe I'll write it out here, I suppose. A3 is equal to base times height over 2, which is just going to be equal to 14. Okay, so that's what A3 is. Good. And what about A2? A2 is just, well, it's a rectangle with a width of 1 and a height of 4. So let's write that out. A2 is equal to, well, 1 times 4, which is just going to be equal to 4. And maybe I should actually color code these things. That's not bad. And A1, which I'll give this red color, I suppose, is going to be, well, this curved area. And that's the one where we're going to need to use our integration. So we want to take the sum. So the sum from 0 all the way to 4 of this function right here. Let's put it in. Negative 1/4 x squared plus 2x, and then we can't forget this dx. And that will give us the area of A1. So let's go ahead and put this into the calculator. So here we are. Here's a calculator. Let's go calculus. In this case, we want to find the numerical integral. And we want to find the sum from 0 to 4 of this function that starts with negative 1/4 and so on. Plus 2x. dx is already given to us. How do we choose that it's dx? It just needs to match the variable. Alright, 10.666 and infinite number of 6's. So we can just write it as 10.7 to 3 sig figs. So let's go back to the document. And this is going to be 10.6666. I'm actually going to write that out. 6666 and then 7 or so. And then 10.7, which is 3 sig figs. Okay. And of course they asked us for the total area. So let me just write that out. Let's go ahead and, oops, I realized that these aren't correctly color coded. This was A3. All right, so area of the total is equal to A1 plus A2, A1 plus A2 plus A3. All right, and that's not too bad. This is just going to be 10.7 plus 4 plus 14. And I'm actually just going to work that out right here. 18 plus 10.7, 28.7, of course. There we go. 28.7, and I guess if we wanted, we could write meters squared as well. All right, 28.7. That looks good. 28.7 is our exact area of this slide. And a nice, what is often a popular kind of combination in a sense, is trapezoid rule, which is an approximation linked with exact, so finding the exact area. And you actually see this a number of times. The last part is percentage error, so how much are we off by, essentially. And that's exactly what part D leads into. So find the percentage error in the total area under the entire model of the slide when using approximate value from part A. So I'm going to clear this up just to make a little more room. Okay. So find the percentage error in the total area. So percentage error, remember, is given to us in the formula booklet. I'm going to write it out here. You can always find it in the formula booklet as well. All right, percentage error. And it's equal to, we want to put absolute values, which essentially says no negatives allowed. And it's approximate approximate or estimate. Right, estimate actually. I think it's maybe easier to remember. Estimate minus exact. So the distance between estimate and exact as a fraction of the exact. And then we say these absolute values means no negatives. If the estimate is bigger or the exact is bigger, we just don't want any negatives. And then, to make it a percentage, we multiply it by 100%. Alright, in this case, the estimate, sorry, the estimate was, what was it? I hope I didn't delete it all. What was the estimate for the trapezoid rule? When we use the trapezoid rule, let me actually just look back here. I can see it. It was 10.5. It was 10.5. That's right. So our estimate was 10.5 in this case, right here. So our approximate A1, or A1 as approximated, was roughly 10.5. So maybe I'll write this out here, but not with all the colors, because I think that would take a little too long. Our approximation was essentially the exact same thing, except this is 10.5, and this would still be 4 and 14. So essentially, our approximation would have been 28.5. And I hope that makes sense. The idea is that this is still a rectangle, and this is still a triangle. So this we can calculate well, directly. There's no error here. It's only in this curved section where we are approximating. So this is our approximation, and this is our exact value. So going down here, once again, estimate minus exact. That'll do. Estimate is 28.5. 28.5. The exact is 28.7, and we want to write it out over 28.7. We say no negatives, that's why we put these absolute values, and then multiply by 100%. Alright, I'm going to go to the calculator and work this out. Actually, I'd use the calculator that I have beside me. 28.5 minus 28.7 divided by 28.7 and then multiplied by 100. Okay, and this gives us a value of 0.696864, so on, so on, so on. So to 3 sig figs, this would be 0.697%. So really small, actually, really small percentage. Okay. All right, great. Not a bad question as well. Okay, that's 3 marks for percentage error. It's kind of involved because we needed to first approximate here. All right, 2 more questions, I think. Good, I think a decent paper too so far. Here we go. So 19 mark question, looks like a statistics question. So here we go. A recent study found that the heights of Dutch women can be modeled by a normal distribution with mean 17.07 and standard deviation 6.3 centimeters. A Dutch woman is chosen at random. Calculate the probability that her height is less than 160 centimeters, between 160 and 170 centimeters. So there's some key information here. They've told us that we're in the world of normal distributions. Oftentimes we can actually read it off. It says normal distribution with mean of blank and standard deviation. And that means that we're dealing with these standard bell curves. And so in this case, we've got a mean, an average of 170.7, then we've got a standard deviation of, in this case, 6.3. So we want to find the probability that the height is less than 160 meters. So remember, for normal distribution, we can get process marks for just shading in an area. So this is 160, and then this would be shading in the approximate area. And we want to find the percentage. So what is the chance, for example, that a individual, in this case a Dutch woman selected at random, is less than 160 centimeters? So let's go to the calculator and work this out. I'm going to get a new window. Menu, go into our calculator, and in this case we want to go into probability and distributions and normal CDF. Our lower bound can be negative, could be 0. I mean, 0 already doesn't really make sense, but we just want to make sure that we've got everything covered to the left of our upper bound, so 160 and everything to the left. The mean was 170.7, and the standard deviation was 6.3. So lower bound, upper bound, mean, standard deviation. This corresponds to roughly 4.5%, or 0.0447. So I'm going to go ahead and go back to the document. I'm going to write this out as norm CDF, and then we can write this, I'm going to write this as 0, 160, and then mean, standard deviation, and then our value is equal to 0.036 figs, 447. Okay, good. Now we want between 160 and 170. I'm going to draw another normal curve. Here we go. This is 170.7, and in this case we want it between 160 and 170, so actually just slightly to the left here. And this is the percentage that we are dealing with. So I'm going to go back to the calculator and work this out. Menu, probability. Here we go. In this case, our lower bound is 160, upper bound is 170. Mean is again 170.7, and our standard deviation is 6.3. Okay, didn't show up. So at the time I was thinking about whether I entered this in correctly, just because on the document I'd written 170 instead of 170.7. Alright, so sorry, let's do this again and make sure that it shows up this time. Normal CDF, okay. Lower bound of 160, upper bound of 170, a mean of 170.7, and a standard deviation of 6.3. And hopefully, there it is. Okay. So roughly, in this case, 41.1%. I'm going to go back to the document and write this out. So norm CDF, this is our lower bound, upper bound, and then our mean, and then standard deviation. And in this case, it's 0.0411. And I guess I can change this. It should be 170.7, which means I need to change this one as well. Sorry about that. Okay, let's go on. Alright. 27% of Dutch women have a height of more than h meters. Calculate the value of h. Okay, not a bad question. Essentially, we're starting off with just plain normal distribution, and then we're moving on into inverse normal. So I'm going to draw another diagram just to show what this looks like. So here is our normal curve once again, and we'll center it at 170.7. And they're telling us that 27% of Dutch women have a height more than h. So this is the 50% line, this symmetrical line which divides it, population, in half. In this case, 27% have more than h. So if we were to draw some line like this, what we would be saying is that there's 27%, only 27% of, in this case, Dutch women have a height more than this value of h right here. And the question is, okay, well, what is that value of h? So in this case, if we have a boundary, that is to say lower bound and upper bound, and we want to find the percent, lower bound, upper bound, find the percent, we use norm CDF. If we're given a percent and we want to find the cutoff point, that is to say we don't have the boundary but we want to find it, we have to reverse the process, or what that is also called is inverse. So you have to take the inverse. So let's go ahead. Before we do that, remember the calculator sweeps from left to right. So although we want to find this top 27%, the calculator, if you put in just 0.27, which corresponds to 27%, the calculator is going to sweep through 27%, whereas 0.27, it's going to stop here. But that would give us the smallest 27%, but we want the largest. So in this case, what we would do is, hopefully this isn't too many colors, we would want the calculator to sweep through, well, this 73% rather, 73% before reaching this 27%. And hopefully that makes sense, that we ask the calculator to sweep through this 73% before reaching this 23 right here. So let's go ahead and do that. So go to the calculator, probability distributions. In this case, we want inverse normal. We want the calculator to sweep through 73% because there's 27 on the other side. Mean is 170.7. Standard deviation is 6.3. All right. In this case, if someone wanted to be in the top 27%, they would need to have a height of more than 174.56 centimeters. So let's go ahead and go back to the calculator. So inverse normal. This is 0.73, 170.7, 6.3, and this is just going to be equal to 174.56, or I guess 170.56, and then to 3 sig figs, this would actually just be 175 centimeters. All right, there we go. Not too bad. Let's see. Let's continue on. Jenneke selects a random sample of 200 Dutch women from Amsterdam and measures their heights. She wants to determine whether this sample could have been chosen from a normally distributed population with mean of 177 centimeters and a standard deviation of 6.3 meters. Okay. She performs a chi-squared goodness of fit test at the 5% significance level, and she begins by creating the following frequency table. Okay. So what does this mean? So this is what she observed. She goes out, she selects 200 people, and she classifies them into these kind of bin widths. 6 of them are less than or equal to 160, 85 are between 160 and 170, and so on. All right. Okay. So this is what we observe, and then if we had this normal distribution with a mean of 170.7 and a standard deviation of 6.3, this is what we would expect. And remember, expected frequency is given by number of trials times probability of outcome. In this case, we have 200 individuals, and we want to know what's the probability that they would be less than 160 in this case. And we can actually do that for every single value here, and that's how we can work out the expected frequency of, in this case, a certain Dutch woman falling within these height boundaries. Okay, so let's look at 160 to 170. Remember, a good IB question often has previous parts leading into the others. So here we had the probability that a Dutch woman would be between 160 and 170 centimeters. And we found out what is the probability of a Dutch woman falling between 160 and 170 centimeters. Whoops, sorry. I'm just looking at my results from the calculator screen right now. Actually, I can show you. There they are. I'm just checking this again, and thankfully I did this graph, but this should be a little higher up. This should be 0.411, not 0.0411. Okay, so that's a little better. Here we are. This is 0.411, or roughly 41% of Dutch women we would expect to be between 160 and 170. So using this formula right here of expected frequency, so we have in this case 200 Dutch women, and we would expect 0.411, or roughly 41% of them, to be between 160 and 170. That's what this means. So between here, there's roughly 41%, or 0.411, and we would expect, based on this, 41% of our sample of 200 to be within this range. So I'm going to work that out on the calculator that I have beside me, times 0.411. Good. And this would give a value of 82.2. So A is equal to 82.2. This is a rather small 2-mark question. So no process marks. If it's just 2 marks for A and B, that's all they're expecting. And then 170 to 180. 170 to 180. It's hard to believe that this is actually a 2-mark question. Do we have 170 to 180? We do not. Okay, so why is this a 2-mark question? I was thinking, okay, what are we going to need to do? We're going to do a normal distribution on this, but what we can do is, we can imagine summing up all of these values should equal to 200. We have 160 as a lower bound going to 0. We have h as an upper bound going to 180, and we have 82, so this would be this last missing piece. So if we know that they all must add up to 200, this is 8.943 plus 882.2 plus b plus 13.99 must equal to 200, and then we could find the missing piece that way. So I think it's pretty light for, or pretty involved for a 2-mark question. I'm going to work that out on my calculator here. So 8.943 plus 82.2 plus 13.99, 200 minus all of this, and that means that B would equal to 94.87 or 94.9. Are they asking this? There it is, 4 sig figs. 4 sig figs. Okay. So let me actually just go back. 200 times 0.411. This is still 82.2. So that's actually okay. 82.20 then. And this, I'm just trying to see if they're asking for 4 sig figs up here, but they aren't. Okay. In that case, it would just be 82.2 plus 13.99, and then 200 minus the answer would be 94.87. 94.87. So one reason why I thought it might be to 4 sig figs after skimming this, and to be honest, missing it the first time around, is because all of these are actually to 4 sig figs. This is 1, 2, 3, 4. This is 1, 2, 3, 4. So I thought, okay. There it is, 94.87. Okay. So this is Yannicka continuing on her chi-squared goodness of fit test. So here we are, just going back all the way up here. She's got some observed frequencies, and she's got some expected frequencies, and from this we can run a chi-squared goodness of fit test. So essentially the question is, to what extent do our expected frequencies align with what we would, to what extent do our observed frequencies align with what we would expect if this were to be a normal distribution. So the hypotheses for Yannicka's test are: the heights are drawn from a normally distributed population. That is to say, it does actually reflect a normal distributed population with mean and standard deviation, or it is not drawn from a normally distributed population. Write down the degrees of freedom. Degrees of freedom, remember, is just row minus 1, column minus 1. Here we are. In this case, we have 1, 2, 3, 4 rows and 2 columns, right? 1, 2, 3, 4, 1, 2, 2 columns. So in this case, we have 4 minus 1, 2 minus 1, or simply 3. The critical value for this test is 7.815. They're asking us to perform a chi-squared goodness of fit test and state the conclusion justifying your reasoning. Okay, so pretty straightforward chi-squared goodness of fit test. So let's go back to the calculator. Go into spreadsheets. We can write x and y, or we can write observed and estimated. I'm going to go ahead and plug in the observed here, which was 6, 85, 92, and 17. 6, 85, 92, and 17. And this is the expected 943. This is 82.20. That's right. I'm just looking at this 82.20 and wondering if everything is okay, but it is. It's what it should be. All right, 82.20, 94.87, and 13.99. So we've got observed and expected. Now let's go ahead and run a statistical test. And in this case, we want to run a chi-squared goodness of fit. Our observed were in the x, our expected were in the y, our degrees of freedom are equal to 3. And let's go ahead and run our test. Okay. Chi-squared value, 1.798. P-value, 0.615. Okay. Let's go back to the document. Okay. We've performed this chi-squared goodness of fit test. I'm going to erase this just because I need the space. And we want to state your conclusion justifying your reasoning. Okay. So they gave us a critical value. I'm not sure if above they gave us a percentage, as in a significance level of 10%. Here it is. 5% significance level. So we can compare the p-value or the chi-squared value. P-value is sometimes a little more standard, so maybe we can do that. So p-val is equal to 5%, or 0.05, and p-crit, what we found, was equal to, or, sorry, let me write this again. Our critical value, p-crit, is equal to 5%, and the p-value we found was equal to 0.615, or we could say is 61.5%. And so comparing these two, this p-value and p-crit, what could we say? Well, we obviously know that, I'm just thinking how we should write this. Let's write it like this. P-crit is less than our p-value, or 5% is less than 61.5. In this case, we often say if p is low, the null has got to go, or HO has got to go. In this case, the p-value is quite high, so in this case we would fail to reject HO. So we fail to reject. That would be our conclusion, and this would be us justifying our reasoning. Okay, so fail to reject the null hypothesis. The other way to do this, we can use the chi-squared critical value. And what was it? The chi-squared value is just on the screen again, 1.798. Chi-squared value is the measure of the difference between the observed and the expected. And in this case, there's actually a little difference, not a significant amount, only 1.798. And our cutoff point was 7.815. That was our chi-squared critical value. So that's how much difference we're willing to tolerate. And we've only found 1.798, which is not that much. So we would fail to reject the null hypothesis again. We can compare either one, either the p-value or the chi-squared critical value. And we want to show the p-value, we want to draw a comparison, and then our conclusion, fail to reject. Or we could say accept, but would maybe a little more proper to say fail to reject. All right, moving on. Gundiger claims that, on average, Latvian women are taller than Dutch women. Random samples of 10 Latvian women and 10 Dutch women are chosen, and their heights are measured. Okay. Gundiger performs a t-test at a 5% significance level. It is assumed that the populations are normally distributed and have equal variances. That essentially means that we write pooled equals yes. Write down the null and alternative hypotheses for these tests, and perform a t-test and state your conclusions justifying your reasoning. Alright, so t-test, we have still the null and the alternative, just like our chi-squared. Null and alternative. Remember, t-test compares means. So let's call this mu1, or mean 1, and let's call this mu2. Alright, so what do we want to see? Gundiger claims that on average, Latvian women are taller. So what does that mean? If Latvian women are U1 and Dutch women are U2, that would give us some indication of our alternative hypothesis. null hypothesis is always status quo. Null, like null, 0, is status quo, no difference. It's the alternative that is more significant, that matters. So in this case, what is the comparison between mu1 and mu2? In this case, Gundiga claims that Latvian women, which we represented as mu1, are taller than Dutch women. So mu1 greater than mu2. mu1 greater than mu2. That's all we need. There it is for part F. Let's go to G. Perform a t-test and state your conclusion, justifying your reasoning. This is a little repetitive, and I'm surprised that they put these just side by side like this. I'm going to go ahead and go to the calculator screen, get a new document, and here we go, x and y. Let's put those values in, 171, and so on, 59, 169. To be honest, I think it's a good idea to check when you write these out, just because it would be unfortunate for such a large question if it was to be a transcription error. 166, and so on. 69, 65, and so on. I'm going to check just real quick, just to make sure that everything is okay. 80, 59, 170, looks good. And then here, 275, 61, 69, 65. Okay, good. Let's go menu, statistics, stat tests. In this case, we've got two samples. We've got a sample of Latvian women and a sample of Dutch women in this case. List 1, we put in the X. List 2, we put in the Y. No frequencies. We said that U1 was greater than U2, that is to say Latvian women are taller than Dutch women. And then pooled for all IB questions, pooled is yes. You won't lose all your marks, but you'll lose, I think, 1 or 2 or so. It's a common enough error that IB actually plans for it, but pooled is yes, always yes. It's easy to remember. Okay, there we go. And let's go and look for the p-value again. And it looks very similar to the last one, very high again. Okay, so perform a t-test and state your conclusion. So let's compare. So we're back at the document here. P-crit, we said was 5%. P-value that we found was equal to 67.3%. So what does that mean? That means that P-crit is less than the p-value. Well, because 5% is less than 67.3. Therefore, we again fail to reject. We fail to reject the null hypothesis. P-value is pretty high, so we don't reject. All right. Fail to reject the null hypothesis. Gundiga's is not correct. It looks like there's no significant difference. All right. Last question. Made it. Make it through this exam. Decent exam so far. This was an exam actually where paper 1 I thought was quite challenging, relatively speaking, and paper 2 is potentially a little more straightforward. Okay, let's see what we can do. So 16-mark question, and this is I believe it's actually pretty heavy, relatively speaking, in terms of algebra, and so let's see. A skip is a container used to carry garbage away from a construction site. For safety reasons, the garbage must not extend beyond the top of the skip. The maximum volume of garbage to be removed is therefore equal to the volume of the skip. So this is the skip right here. Not this part, but just this part that can be carried. We can't overflow it. it'll fall out. A particular design of skip can be modeled as a prism with a trapezoidal cross-section. So here we've got this trapezoid. For the skip to be transported, it must have a rectangular base of length 10 and width 3 meters. The length of the sloping edge is fixed at 4 meters and makes an angle theta with the horizontal. The following diagram shows such a skip. Okay. Find the volume of this skip, and they give us a few different scenarios, and it's 9 marks here. Find the volume of the skip if the length of the top edge of the skip is 11 meters. Okay, so if the top edge of this is 11 meters, what's the volume? First off, volume of a prism with uniform cross-section is just going to be, maybe I'll draw a quick sketch, is just going to be, of course, length times width times height. In this case, we're not dealing with just a prism, we're not dealing with a rectangular prism. This face here is a trapezoidal prism. So usually trapezoids we would present like this, for example, something like this. And the formula for the area of a trapezoid is AB is the average of these two horizontal or parallel lines. So A plus B over 2 multiplied by H, and that would be the area of a trapezoid. And so if we want to find the volume, in this case, of this trapezoidal prism, we can use, in this case, not length times width times height, but area of one of these faces. So in this case, like this, area of one of the faces multiplied by extension. Or another way to express volume is area of cross-section. Sometimes we write area of the base times height, but really we're talking about area of any uniform cross-section, in this case this front face here, multiplied by extension. So that's essentially what we're doing here. If we can find this face right here, the area of this face, and then multiply by its extension, that is to say by 3, then we can find the volume. So let's go ahead and see if we can do that. I might actually leave this just because I think it will be helpful. Okay, so the first part they're asking us if the length of the top edge of the skip is 11 meters. So if this right here is 11 meters. So maybe I'll use a blue still. So if this right here is 11. So we actually don't know what the height would be yet. So how can we calculate this face right here? Now, we already went in and looked at what the area of a trapezoid is. It's average of the top and bottom multiplied by the height. So A plus B over 2 multiplied by the height. In this case, we know the area of this face. So I'm going to write this as area of the, let's actually write AT for area of the trapezoid. It's going to be equal to 10 plus 11 over 2. So we know one side and another side over 2. We want to multiply this by the height. But the question is, well, what is the height? And this is probably why it's the final question on paper 2. The height in this case would be, well, just this value right here. This would be our height. But, well, what is the height in this case? Well, we know that this right here is 10, this right here is 11, so we know that this right here is going to be the difference, and it is going to be equal to 1. And we also know, might need to make this a little thicker, but if this value is 4, this sloping edge, then this also is going to be, oops, I think I can do better than that. This also is going to be this is going to be 4 right here as well. Let me just try to draw a line. This is also going to be 4. So in order to find the height right here, since we have a right angle, since we've drawn it right up, and these are parallel lines, this has to be a right angle as well. So we have, well, the hypotenuse, and we have a side length, but we don't have h. So let me write this out and potentially try to write this out. This is 1, this is 4, this is h essentially, this is what we're dealing with, and we have h squared plus 1 squared is equal to 4 squared, or just getting h all by itself, this is 4 squared minus 1 squared, or just 1, and h is equal to the square root of all of this business, 4 squared minus 1, 4 squared is 16, 16 minus 1 is just going to give us 15. So that's our height. Okay, the height is equal to root 15, or 4 squared minus 1. Okay, so that would be the area of this face right here. Or this, see if I can use this fancy design. That would be the area of this face right here. Okay, and if we multiply by the extension, then we can find the volume. So volume is area of the face, the uniform cross-section, multiplied by the extension. So if we want to move to volume, volume is equal to area of the face times extension. In this case it's 3, or let's write that all out in one big equation almost, I suppose. So 10 plus 11 over 2 times root 15. I'm actually going to open up some brackets because we want to multiply this. This is just the face by 3. Okay, and I think we should be able to work this out using our calculator. So let's go to the calculator here and let's open up some brackets, I suppose, and get a fraction. 10 plus 11 over 2. And we're going to multiply this by the square root of 15. Oops. Don't need the square. Square root of 15. And we actually want to multiply everything by 3. We could actually just multiply this by 3 and it wouldn't change anything, but just for the sake of consistency, multiply by 3. Okay. So this is area of the face times 3, and it is 121.999, or to 3 sig figs, just 122. So going back to the document here, volume is equal to 122. Okay, not bad. If the height of the skip is 3.2 meters, so find the volume of the skip if the height of the skip is 3.2 meters. So let's clear this up. We found out the first situation where the length of the top of the skip is 11 meters, and we found that unknown for the height. Now we want to see if the height of the skip is 3.2 meters, what would be our volume. So I'm going to clear this up. I don't think we need any of this actually, so I'm just going to completely erase all of this. Okay, so now they're telling us that the height of the skip is equal to 3.2. So in this case, the height, oops, I guess I could have left that. The height in this case is 3.2. And in this case, what is the volume? So, all right, let's see. Once again, we're actually dealing with this right angle triangle. We know for a parallelogram, it's going to be the top, so these two horizontal lines, so A and B. We know 10 is here, and we know there's going to be 10 right here, but the question is, what is the total length? So if we add on to this, what is the total length of this top of this skip? Because that's what's important. We need to find both horizontal side lengths, I suppose. Alright, so let's find out what this is right here. Let's call this maybe x. So once again, we drew an angle to the top, and it's a right angle. This is actually kind of strange because it's very similar to the previous process. Going to draw a triangle here once again, and right angle. This is 3.2. This side length, similar to before, is 4. This will be called x. So I'm going to rewrite this Pythagorean theorem: x squared plus 3.2 squared is equal to 4 squared. Let's bring x squared all to one side. 4 squared minus 3.2 squared. You could actually just end solve for x, and that would be okay as well. And just keep a few decimal places. Alright, so what is this value? This value is actually the square root of 4 squared minus 3.2 squared. Okay, so let's go ahead and work that out. If you're comfortable converting that, approximating it to a decimal, and then going from there, you can certainly do that. Just make sure to keep enough significant figures. I'm actually going to work that out on the calculator that I have right beside me. 4 squared minus 3.2 squared, and then the square root of that. It actually approximates pretty nicely to 2.4. That's the actual value, actually, 2.4, so without any kind of approximation. And that's actually kind of nice. So the overall top length from here to here would be 10 plus 2.4, or overall 12.4. So once again, drawing on this idea of area of a trapezoid, bottom plus top divided by 2 multiplied by height. So let's go ahead and find the area of the trapezoid. So bottom plus top, 10 plus 2.4, divided by 2, multiplied by height of 3.2, and then multiplied by extension of 3. Alright, let's work that out. Here we go. Actually, I'll work it out on the calculator right here. So, open up bracket. We've got 10 plus 12.4, over 2, multiplied by 3.2, and then put some brackets and multiplied by 3 again. In this case, it would be 107.52. So, heading back to the document here, 107.52, or to 3 sig figs 108. Okay. Not bad, not bad. And it's close enough to the other value that it doesn't seem absurd, which is always reassuring. So 108 meters cubed, that would be our volume. Let's do the last one here. If theta is equal to 60 degrees, that is a nice question. If theta is equal to 60 degrees, okay, so let's go ahead and erase this, clear up some space, and if theta is equal to 60 degrees, then what is going to happen. So once again, let's draw this right triangle. We know that this from here is going to be 10. And the question is, what is this extension right here? Maybe I'll use a different color even. This extension right here. What is this value? Once again, we've got a right angle triangle. And in this case, they're telling us that this theta value right here is equal to 60 degrees. Okay, so what can we do with that? What can we do with that? And what do we know? What do we know about this? We don't know the height, but we do know that this is 4. So to complete our triangle, once again, we know that this value is equal to 4. And where does that 60 degrees come from? So I guess one thing that we could say, maybe the simplest way, is we could say, hey, straight up from the base is 60 degrees, and that means what must be left over is 30 degrees, because it must add up to 90. Another way to do it is we could say, hey, we've got Z angles, and we could say this is 60 degrees as well. Either way would work, as long as we can use these. I'm going to actually use this 30 degree in the bottom. Okay, so using this 30 degrees in the bottom, we've got an opposite side length, and we've got the hypotenuse. So if we want to find x, we can use a sine ratio. So remember SOHCAHTOA. So we've got sine 30 degrees is equal to the opposite over hypotenuse, and then just a little rearranging. 4 sine 30 is equal to x. Sine 30 is actually equal to a half, so this is just going to be equal to 2. So x is actually just equal to a 2 in this case, which is, that's kind of nice. Alright, so let's go ahead and complete this. So this value is equal to 2. Let's write out the area of this trapezoid once again. So here we are. Was the first one 12? No, the first one was 11. I thought it might be the exact same. So the side length of the bottom plus 10 plus 2 is 12 over 2 multiplied by, we don't have the height yet. Don't have the height. I guess we could use Pythagorean theorem for the height, or we could use trigonometry. I'm going to use Pythagorean theorem just because I think it's potentially a little more straightforward. So here again, we've got 4, we've got 2, this is h squared plus 2 squared is equal to 4 squared. H squared is equal to 4 squared plus 2 squared. And that means h is equal to the square root of, whoops, so I did this a little quickly, minus 2 squared. 4 squared minus 2 squared. Or 16 minus 4 is just going to be root 12. Okay. So that's our height, essentially, is root 12. And then this is all multiplied by the extension of 3. So once again, we've got a trapezoid. The bottom length plus the top length divided by 2 multiplied by the height, which we found just using Pythagorean theorem in this case. And then we multiplied this by the extension. And I'm going to work that out on the calculator here. Let's see. Open up some brackets. And here we are. 10 plus 12 over 2. Multiply all of this by the square root of 12. Close some brackets, and then multiply this by 3. This gives us 114.315. So heading back to the document, 114.315, or to 3 sig figs, 114. Okay, we're really almost done, actually. 5 marks to go. Explain in context why theta cannot equal 0. So let me just erase this real quick, just to hopefully give a better indication of what's happening here. So why can't theta be equal to 0? So this is theta right here, and this is theta increasing, and this is theta decreasing, and this is what theta would be if it was 0. And if theta was equal to 0, well, looking back at this skip, that would be like, well, it's horizontal with the ground, and as soon as like the driver puts the accelerator on, all the trash is going to fall out the back. So why can't theta be equal to 0? Well, explain in context, the garbage would fall out. The garbage would fall out. And just in case you are thinking that that is a ridiculous thing to say, here is the mark scheme. Here it is. The skip would have 0 volume, that's right. It wouldn't hold anything, so it'd just be flat, or the contents would fall out. That's true. That's what would happen. Okay. Last question here. We're asked to sketch this function, this 24 sine theta, open bracket 5 plus cos theta, for 0 to 90 degrees. So from 0 to 90 degrees. And then after that, we're finding the maximum volume of the skip and the value of theta for which this volume occurs. Okay, so let's go ahead on the document and graph this. Make sure we're in degrees, this will matter. 24, in this case, sine. Let's call it x, we don't need to call it theta. We actually need to call it x because this is x, f of x, we've defined it as x. 24 sine theta, then multiplied by 5 plus, in this case, cos theta. There we go. And remember, going back to the document here, they asked us from 0 to 90 degrees. So let's go ahead and change our window. You can actually see what happens if we just zoom out and see if that does anything. That's actually not too bad. 0 to 90 is what we're actually interested in. So we could change that if we wanted. But here's our graph. Sketch the graph from 0 to 90. So actually, just going to look at the value. So menu, trace, graph trace. What happens when we are at 90? When we're at 90, we've actually started coming down a little. We're at 120. So one thing I'm going to do as well is I'm going to find where the maximum occurs and then trace for that endpoint of 90. So here's when 90, we're at 120, and the maximum occurs at 79.27, and it's at 122. So sketch, we want to show our main, our critical points in some ways. So heading back to the document here, I'm going to draw a sketch. And in this case, we need to show the rough shape of the curve, the maximum, and then say the endpoint as well. So we travel through the point 0, 0, we come up, and then it looks like we kind of go off right here. The maximum we found was 79.3, and at 122, and this endpoint right here was 90 and 120. Okay, just want to give an idea of what a sketch looks like. Here's the mark scheme. So showing where we intersect this 0, and then this endpoint of 90. So correct shape and the graph of the correct labeled domain. So we go up to 90. All right. Okay. So condone omission of theta and volume. So labeling our theta, labeling volume, or xy potentially. We could use it, but theta and volume is better. So I'm going to go back to the document here, and this is maybe more complete. This is theta, this is volume. Not a bad idea to put arrows here. Here's our origin that we go through, and this is the endpoint of 90. I think this already shows that it's 90. Alright, find the maximum volume of the skip and the value of theta for which this occurs. So this is already volume against theta. So our maximum volume is equal to, well, the y value right here of 122, and it occurs when theta is equal to 79.3. So just going back to the calculator, it's this maximum right here. When x, or when theta is equal to 79.3, our volume is equal to 122.2. So here is D1, this is D2, the maximum volume of the skip. So max volume is equal to 122.3 or 29. Let's leave it at 1.22. And then I think it's meters cubed, is it? Meters cubed. And then the theta value in this case would be 79.3 degrees. All right. I think that is good. Maximum volume of the skip and the value of theta for which this occurs. Good. I think that's it. I would just say one last thing. So usually the questions get more challenging as you go through this, and by and large that was the case. But for this final question, sketch the graph and then find the maximum. So this is a final 4 marks on this test, and it really is just, plotting the graph, zooming out, and then showing the max, finding the max, and well, just showing that we know what it means in context. X is theta and y is volume. So always, I think, in a paper to look for kind of entry points, and this is one of those examples. So all the way at the end, sketching the graph, finding the maximum, and then just putting those values. Nice kind of 4 marks. Okay, everybody. Hope that was helpful, and best of luck as always. Take care. Bye-bye.